Dobrý den, já jsem Giovanni Gherdovich a já pracujem v SUSE, and that's all my check. So I'm sorry, but this talk is going to continue in English. We are here today. Thank you for coming, first of all. Again, I'm Giovanni Gherdovich. I work at SUSE. We're here today to talk about dynamic frequency scaling of the CPU on Linux. Before we begin, SUSE is hiring, so if you like, check the website suse.com/jobs. This is the agenda of the talk. We are going to start with a brief overview of power management, then present the meaning of the terms governors and frequency scaling drivers, and then examine more closely a couple of governors and the algorithms they use to affect the frequency of our CPU. And feel free to interrupt me anytime with any question. So some of you may already have heard about frequency governors, frequency drivers, and might want to check right now what is running on your laptop or maybe at home on your desktop. Those are the commands that you can use to know immediately what are the first command, CPU power --CPU frequency info --driver will tell you what is the kernel driver that is currently talking to your CPU for frequency scaling. The second command, --policy, will tell you what is the governors that you're running right now. And the last command, --governors, will tell you which governors are available on your system that you may choose to use. If this content does not make much sense to you right now, hopefully become more clear by the end of the talk. So what is power management, and which part of power management are we addressing right now? We are talking about active power management, which is opposed to idle power management or static power management, which happens when your machine goes to deeper sleep state. Active power management is what we do while we are running instruction, while we are executing code, while we are doing useful work. But we try to do it saving some energy. So the definition, you can read it on the slide, is we do this by scaling voltage and frequency of the CPUs to consume as little power as needed while guaranteeing acceptable performance. The last part of this statement is necessary, obviously, because if you remove it using as little power as needed, you can just shut down your computer. But this is not what we're talking about now. We want to run a useful workload and try to save some energy while doing that. So this formula is important for our consideration, which is the power that is consumed instantaneously by your CPU. And as we can see, we can make a couple of remarks. First off, this power is quadratic with respect to the voltage that we apply to our CPU. It's linear with respect to the frequency. And there is this additive term, power static, which is the power consumption of our CPU while it does nothing. So it's a constant component. And something that is not written in this formula, but we have to consider, is that voltage and frequency move together. So while it is technically possible to set them independently, you cannot expect to rise your frequency and do not give more voltage to the CPU. The CPU will not work as intended. So so voltage and frequency are parameters that in some sense have a linear dependency on each other. So you rise the frequency, you have to rise the voltage. So if you want to rise the speed of your CPU, you increase the frequency, you have, as I just said, to increase the voltage, and there you have a quadratic increase on power consumption. Looking at this formula, we can also make another remark, which is one could intuitively think about, I will halve the speed of my CPU, and then the workload that I'm interested in will run in double the time, because I'm going half as fast, so it will take double the time. So at the end, the energy that I consume is the same. But this is not true because of this quadratic relationship. So it is interesting actually to try to go a little slower at a little lower frequency and then a little lower voltage in order to save that power. And this is, I hope you can read the text in this slide. So this is Theodore So, a kernel maintainer in the file system area. In 2013, he asked to some power management expert on Google+. He said, some people in the office are saying that the on-demand CPU governor is actually counterproductive. So the on-demand one is the one that tries to balance the power, so reduce the power if the CPU is not under load. So it should save power. Is actually counterproductive because waking up to decide whether the CPU is idle keeps it from entering the deepest sleep state. And so, counterintuitively, the performance governor, which is the one that always sets you to the max speed, will actually result in the best battery life. So this was a question that he posed, and he was answered by Anjan van der Waal. And the scenario that Theodore described is called race to halt. And it's based on the assumption that the power that I consume while the CPU is halted is really, really low. So it's actually advantageous to try to do all the work I have to do as fast as I can and then stay in this idle state so that I can save power. But is this a viable strategy? Some things, these are some arguments and counter-arguments for racing to halt. So your idle power needs to be really low. And this happens since recent processor. Then there is another consideration, which is instructions such as reading from memory will not execute faster when you increase the frequency of the CPU, because the memory just not get faster. So they will run at the same time. So your race to halt is not going fast. And then this phenomenon of racing to halt contributes linearly to your power saving. As you see, if the frequency is 0, the power is linearly dependent on the power static. But your power consumption is quadratically depending on the voltage. So we have a quadratic dependency versus a linear dependency, and at some point for high enough frequency and then high enough voltage, because we just said that frequency and voltage have to change together, this quadratic dependency will catch up on the linear one. And then there is the ACPI standard that is too simplistic for modern microprocessors. So what was contained in that answer is the information to Theodore that a new driver was in the work, and it was actually merged in Linux 3.9, and it's called Intel PState. So what are PState, by the way? The ACPI specification describes several kinds of states. We have global states and so on. The one that interests us are the P states and the C states. C as in CPU power state and P state as in performance state. So the state called C0 is the only one where the CPU is executing instruction. So while we are in C0, we can then fine-tune and move to a lower P state, which will save us some power. And well, again, the definition of a P state is a couple of values, voltage and frequency, and then each logical core of your machine can go at a different P state, which is interesting. So think about two hyper-threading siblings which run a different frequency, and this happens. Again, voltage and frequency grow together. They must grow together. So a P state is a couple of value, voltage and frequency. What is a governor now, and what is a driver? So a governor is the piece of software that decides if we have to change the frequency of the CPU and what is the next frequency value. And the driver is the piece of software that implements this decision. The CPUFreq subsystem was designed initially with the idea that governors and drivers should be somehow orthogonal. So you could choose your driver and choose your governor independently. So in this matrix that I draw, you could choose any driver, such as ACPI, CPUFreq, and then one of the available governors, and position your machine at that point in the matrix. Intel PState does not work like that. And it does embed both the governor and it has both governors and a driver. So it breaks this sort of modular architecture, and the Intel engineers who designed that said that these policies that have to be implemented by governors are anyway architecture specific. So this design where governors are pluggable was flawed anyway, and it doesn't hold true on today's machine. Sorry. A little bit about names. So we have generic governors, as I said, and we have a list of those that are available. And one is called performance. I mentioned this earlier, and this is the one that always gives you the max frequency. It's not very interesting, but it's very often used in server workloads because people don't want surprise, don't want a governor that does not work as they expect. And then we have power save that always give you the minimum frequency. Intel PState have governors, which are different, but have the same name, so this is a bit confusing. The performance governor in Intel PState works more or less the same, so it gives you the max PState all the time, but the power save is not at all one that gives you the lowest frequency. It is instead the one that implements all the smarts, all the algorithms of Intel PState. So this naming choice was a bit unfortunate. Now let's examine a couple of governors. First off, PState itself with power save that I just mentioned. So why is this governor working so well? Very simply put, because it reads to a model-specific register from the CPU that gives a very accurate value about the past load of the CPU. So the secret sauce is this. It's not an algorithm. It's the fact that it can talk directly to this register of the Intel CPU and gets very accurate data. And the algorithm that implements is something called proportional integral derivative controller, which is a bit of a mouthful, but it's an elementary mathematical device in control that tries to keep a value that you want to achieve, and this is called in PID controller speak, it's called the set point, and then it measures the actual value of this quantity that you want to control, and it computes the error, so the difference of these two, the expected and what is actually on the device. And then it computes a correction, and this correction is the sum of three terms. One is proportional, one is an integral, and one is a derivative. There is a physical justification, intuitive also, to this sum, but at the end of the day, Intel engineers decided that those two terms, B and C, do not work very well, and they set them to 0. So if you look at your kernel, you may be running PState right now, you may be running the governor power save right now, and there is a debug interface to see the parameter of your PID controller, and the integral term and the derivative term are set to 0. I'm sure that they tested this a lot, and they saw that it was the go-to mechanism to perform this kind of activity, this kind of control. But then it probably they had trouble in managing the B and C parameter, and they said, okay, let's shut them down. So now I would like to introduce this concept, and it's the difference between load and utilization in a machine. So in this diagram, I represent on the right CPUs, and those balls are tasks, okay? So you can see that CPU 0 and CPU 1 are processing one task each, okay? And what I represent on the left of the drawing are tasks that are waiting to be run on those CPU. They are in the CPU run queue. So utilization is what the CPU sees, and the CPU only know what it's doing now and what it's doing in the past. It cannot know that the scheduler has plans for the future. So the CPU in this situation will tell you that the system is, the utilization is 50% because we have 4 CPU and 2 are working. But the scheduler knows something more. The scheduler knows that there are run queues that are full of tasks that are going to be run on this CPU. So this is the load of the system, which is a more complete picture of what's going on. And the PState driver that we just saw is actually using only data from the CPU, and it's not profiting from knowledge that is in the scheduler. So this is why in Linux 4.7, a new governor, a generic governor, was introduced called schedutil, and it does use knowledge from the scheduler, which is the load that I just described. In this code, pseudocode, I'm calling it util because it's the name that is used in the code. And throughout the kernel code base, naming is not sometimes very consistent. But the idea is this data, this input, which is util raw, is from the scheduler. And probably the last idea I want to introduce is this frequency invariance, which is something that one have to consider in this kind of situation. So think about a CPU that is running at half its frequency, but the tasks that are to be run are enough to keep it busy all the time. So when you ask the CPU, how busy are you? The CPU will tell you, I'm 100%. So you will think that this CPU is very busy, but it's actually running slow. That's why it is at 100%. So this sort of information is not frequency invariant. So we should scale the information that we get from the CPU utilization by the information of how fast the CPU is actually going. And this is what happens in the schedutil formula. So you have this UTILFreq invariant, and that utilize the data util raw, that the load that the scheduler has computed, and it scales by the ratio current frequency divided by the max frequency. And then, simply enough, the next frequency is going to be the ratio, this invariant load, frequency invariant load that we just computed, divided by the maximum CPU capacity, and then we multiply by the max freq to get into the scale. And so this is how the schedutil governor, which is as of now still a bit experimental, but it's one of the development direction, utilizing information that comes from the scheduler to help decision about which frequency should we run our CPU. And I believe that we are now at 20 minutes, which was the time I was allotted. So I encourage questions. This is what we talked about. We talked about active power management, so no suspend resume, no idle power management. We defined PStates. We know that they are couple, voltage, and frequency. We learned about this fundamental formula that tells us how much power, instantaneous power, is consumed by CPU. The energy is the summation over time of this, or the integral over time of this formula. We know what the governor is, what a driver is, and then we have seen doing frequency scaling with data coming from the CPU versus a more accurate picture of what's happening, so data coming from the scheduler. And we, I believe, had 10 minutes for question.
Thank you. My name is Pavel Pisha, and I would want to ask if you somehow count the statistic of CPU efficiency at a given frequency. Because what you want, in the fact, is to go as fast as possible, but not to lose the cycles like bubbles in the pipeline.
Yes.
So basically, instead of working with all that loads and statistics and so on, try to keep the CPU at such frequency that there is, not so many bubbles. Because if you consider that the access to the external memory takes 100, 200 clocks, and in one clock the CPU is able to process 6 instructions, then basically those bubbles takes or can take more time than whole other processing of the CPU. So if you can write some controller which keeps this level at reasonable value, then the CPU should be most efficient.
Yeah, this is an interesting thought, but I don't see how, because you remove bubbles from the pipeline by reordering instruction, basically. I don't see how running faster or slower could you... Oh, this is true. Now I see. Now I see, because the memory is constant speed, and then the instruction, I mean the instruction that like add, that can actually run faster, would pass on. And that's cool.
And CPU has the statistic, Intel has the statistic counters for this. So basically, I'm not expert at this, but I know that they have the counters that you can count the statistic of utilization. So if you have hyperthreading, then it can utilize somehow the time when one CPU accesses the memory.
Yes.
For sure, you cannot tune it at the level when there are no bubbles, because you are at so low throughput that basically you kill the CPU.
Yeah.
But if you keep it somehow that there is no long time when there are full of bubbles, then basically at this moment...
Yeah, honestly, I wouldn't be surprised if what Intel is doing in the values that comes out of these magical registers is exactly something like this. I mean, the performance that they...
But it cannot be done linearly, because if they use a linear control theory, then it cannot work.
Oh, right.
Because if they are using PSD controller, then basically it controls average level.
Yeah.
Basically, they go too low, maybe.
Yeah, and they actually using a much simpler version of that, because the 2 parameters are 0.
Okay,
so,
but then it is...
They're proportional,
So because they need somehow to change the frequency to follow the data access pattern of the application, even if the application is, for example, running in PREM model, predictive execution model, which, okay, I'm from real-time area, so you even can ask the applications that they say when they would have many page files or many cache files.
Yeah, there is one consideration. This is very interesting, and what I see from the controllers I've seen is not that at all. It's much simpler, and the reason is that because this stuff have to run in scheduler hot path, so they want to have something that is like a few arithmetical instruction, a few.
Yes, but for example, if you write the I component, integrative component, such a way that the increasing goes 2 times faster than decreasing of the frequency, then such non-linear element can change the behavior, maybe, or you can use some predictive controller. Or
that's very interesting. I mean, thank you. This is great stuff. I didn't. Something to think about. Yeah, thank you very much.
Thank you.
Any other? We have 5 minutes, I believe. Otherwise, I have some extra slide. I don't know. Any question? I mean. I don't want to discourage people from speaking. It's actually the interesting part.
I would like to ask you, because is there any difference, like how this is controlled depending on how many cores you have? Like, does Linux differs when you have only 1 core, or when you're running it on a server? Is it
so there is no difference. I mean, this stuff is made for symmetric multiprocessing. So machine with just 1 core, they don't. And yeah, it's an interesting question, because you have you might have a laptop which has 4 or 8 cores, and you have a very large node computer that could have 1,000 core. No, there is no difference in how the scheduler behaves, but there is for sure going to be a difference with respect to mobile platform, like, such as obviously ARM, where they have a completely different architecture, this that I call big little, which couples a CPU that can consume very little power but is slow, and one that can do more computation, but it's actually it's fast, but it consumes a lot of power. So there is a project that ARM and Linaro are pursuing to address exactly this kind of scenario, and it's mostly to accommodate for mobile. And so about in the supercomputing world, people set the CPU frequency governor to performance. They say it's just easier. I mean, I don't want problems. This is sort of a direction of research that, of course, it's necessary when you are on a battery, that we hope that in the future also the enterprise computing servers and so on could benefit from. But at the moment, if you talk to somebody who's doing computing, they say, no, I mean, of course I set it to performance, I set it to the max PState all the time. Even when I do benchmarking, I just want to eliminate one of the variables. It's complicated to think about frequency scaling. But it's something that some people are thinking about, and we all hope that one day you could just use it and don't think about it. But today it's not yet the case.
Yeah, I might not have understood well how the PID is set. What is the set point, or how do you calculate the error for?
Yes, yes. So this is the formula. The idea of a PID is exactly as when you are driving a car. Like you are actually, there is a feedback loop in your perception. Okay, so you want to go straight. So your set point is in the center. Okay, but you might. So if you see that your car is not going where you want it to go, sorry. Now I get it. So yes. Yes. So the set point is the load of the CPU. So let's say that you put as a set point 50% of load, okay? And then you see that the CPU is actually 40%. So you say, wait, I want to decrease the frequency so that because you're going too fast. So I decrease the frequency because. And then your load increase because you're slower and the task fills you. So actually the set point is, sorry, I didn't get a question. Yes, that's, yeah. It's the load. Yeah, sorry. Okay. No, this is and about this. An example of this. What is the set point in our case? Is so the default set point for Intel PState is 97% of load. So this is what they do, and which means that if you are going, I don't know, 80% of load, you're I'm thinking that you are going too fast because tasks are not filling you, so I decrease your frequency so that your load increase. But we on the SLE kernel saw that this was not reactive enough. So instead of setting the set point to 97% load, we set it to 40. So it comes. Yeah, exactly. Yes, because. Again, because we saw in a few workload that it's something that our customer will not tolerate. They say this is low, so we set it to a lower value. But there is a lot of development to be done. It's just the early stage. Thank you very much.